An elastic collision is defined to be a collision in which kinetic energy is conserved. Now that's a pretty vague definition when it comes to trying to figure out if a collision in a problem is an elastic collision. The clues that you're looking for in a problem are things like the words frictionless. So that means no energy would be lost to friction, and that the objects don't stick together during the collision for any period of time or for any reason. So a collision that's an elastic collision might look something like this. Initially, we have these two objects working together. We have velocity 1 going this way, mass 2, velocity 2 going that way. They have some total energy. We have the frictionless surface so that we know there's no loss of energy there. After the collision, we have mass 1 with velocity 1 moving this way, mass 2 with velocity 2 moving that way. Their total momentums are going to be the same on either side, but also that initial kinetic energy that we had over here, if you totaled up their kinetic energy and you totaled up the kinetic energy here, you get the same kinetic energy in both places. Notice that they're bouncing off of each other, right? They're not sticking together. That's a good clue to us that this is an elastic collision. So here we have an elastic collision with these two objects, one moving at 4 meters per second, the other initially at rest with different masses. So we set up our equation m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Now, we run into a little bit of a problem. We know our initial velocity of that one is 0 at rest. But these other two, we don't know either of these final velocities, so we're kind of stuck for the moment. So we'll have to go to kinetic energy and realize that in an elastic collision, kinetic energy is conserved. So I have 1/2 mass 1, velocity 1 squared, plus 1/2 mass 2, velocity 2 squared, equals 1/2 mass 1, velocity 1 squared prime squared plus 1/2 mass 2 velocity 2 prime squared. Now, I know that this is going to be 0 because they're at rest, and so what I want to do now is solve for one of the velocities in one of these equations, and then I can plug it into the other. Now, I don't want to have to deal with the messy squared terms when I'm doing this, so I'm going to start with my momentum equation and solve for, let's say, v1 prime. So v1 prime, based on my conservation of momentum equation, well, I would take m1 v1 minus m2 v2 prime divided by m1, and then I could substitute that in for v1 prime in my kinetic energy equation. So I'd have 1/2, well, actually, we could even take a little step here and say that, well, I have 1/2 in every term, so my halves are going to cancel out. Like that. And so I have m1 v1 squared equals m1. Well, now I'm going to substitute this expression in for v1 prime squared. So m1 v1 minus m2 v2 prime over m1 squared plus m2 v2 prime squared. And now we have just our v2 primes, and so we can start to work with that and figure things out from there. Now, the algebra from here is a little bit messy. I'll leave that to you to start to figure out. We'll also go over it in class a little bit. But if we plug in our numbers and solve everything correctly, we would be able to get an expression or a value for v2 prime, so we know how fast that was going, and once we found v2 prime, we could plug it back in here and find v1 prime. So that would be the process for solving this problem. Seems complicated, seems tricky, but the reality is any elastic collision where you don't know the velocities afterwards can be solved this exact way. So it's this exact setup every single time. So if you can learn how to do this setup, you can solve any elastic collision problem where you don't know the final velocities. An inelastic collision is a collision in which kinetic energy is not conserved. So we're losing some sort of kinetic energy somewhere. That means there's friction involved. things are bouncing off of each other and making noise. Pretty much any real-life collision ends up being some form of inelastic collision where we're using it. If we have a perfectly inelastic collision, something called a perfectly inelastic collision, we have objects stick together. So that's going to be a big clue for you in the problem, is that objects stick, or that friction is involved, or something is involved that causes us to lose energy. If that's the case, then it is an inelastic collision. So let's look at a quick example of that. So here I have two objects of equal mass, so both mass m, one with a positive velocity, one with a negative velocity of the same value. So we have our overall kinetic energy, those things moving together, and they're going to move together and collide. After they collide, we end up with a situation like this, where their velocities are going to cancel each other out, right? They both had equal and opposite velocities, and they're equal masses. So my total momentum is 0, so they're going to hit, they're going to stick together and stop. Now, if we look at kinetic energy here, the kinetic energy here would be some value. Even though this is negative v, it's velocity squared, so that gets rid of that negative there. So it'd essentially be mv squared times 2, so that's why they say the total kinetic energy is just mv squared, not 1/2 mv squared. And over here, because nothing's moving, our kinetic energy is 0, so we've lost kinetic energy through this collision, so that's why it's an inelastic collision. Quick sample problem here. So let's start with our equation, m1 v1, not equals, but plus m2 v2 equals m1 v1 prime plus m2 v2 prime. And we know that the astronaut is initially at rest, so he's m1, we'll call him m1, so that's 0. And afterwards, when the astronaut catches that wrench, that means that their masses are sort of combined now, which means they're going to have the same velocity moving together. So that means that v1 prime and v2 prime are the same thing. So we're going to write our expression this way now, that m2 v2 equals v prime, their total combined velocity, times their combined masses, m1 plus m2. And that's our final momentum of the system, is the two of those things together moving at the same velocity. So mass 2, we have our 1 kilogram wrench thrown at 2 meters per second. And that equals our velocity prime, what we're looking for, times their combined masses, so 80 kilograms plus 2 kilogram, or plus 1 kilogram. And then we're solving for velocity prime. So 1 times 2 is 2, and then 2 divided by 81 gives them a velocity of 0.025 meters per second. And so that would be the velocity of those two things moving together.